In today's video, here is a nice problem. It's coming from the Bulgarian Mathematical Olympiad, edition 1998. Here is the following setup. Suppose m and n as natural numbers. Here is the following fraction. Capital A equals m plus 3. All is raised to the n as an exponent plus number 1. All is divided by 3m. Okay, is an integer. So the question we are going to prove this fraction is an odd integer. Okay. In fact, this is very nice and interesting problem to work on. I'm so excited to work on this problem. So you guys, you can give the hands to this problem prior to the solution. Go ahead, pause this video when you come back to see the full solution. Okay. By the way, don't forget to hit the subscribe button and support the channel by like, comments. Okay. So anyway, usually the method that we apply in this type of problems, we are going by the way of contradiction. So since you have been asked to prove this one is an odd integer, we are going to assume this one is even. At the end of the term, we will find a contradiction. Okay. So this is the best way to go. Okay. Before we get started, we need to check the parity of n. We need to prove the parity of n whether it is odd or even. So this one is an integer equivalent. I'm going to, by multiplying side by side, I get here 3m capital A, which equals m plus 3, all is raised to the n as an exponent plus number 1, like this. Okay, we know the left hand side of this equation is a multiple of 3, so I'm going to reduce this equation to the mod 3 for both sides. Okay, so this one is clearly is giving us is a congruent to 0 mod 3. Okay, then taking number 1 over to the right of the congruence, so I get here m plus 3 to the n is a congruent to minus 1 mod 3. Okay, also this number 3 will be reduced to the mod 3, which is 0. Okay, so I get here m to the n, which is a congruent to minus 1 mod 3. Okay, so I'm going to go by the way of contradiction. Let's assume this n is even. Okay, so by the way of contradiction, suppose n is even, which is going to be written on this form: 2n equals 2c, like this. Okay, now let's plug this number here into this exponent. So I get here the following. I get here m to c, all is raised to the 2. Let's replace m to the c with some integer like a to a square, like this. Replacing mc with a, I get a square is a congruent to minus 1 mod 3. Okay, so I have ended with this nice expression here. Now let's go through quick chart to see what's the possible values of e square as a reminders when you reduce this one to mod 3. Okay, let's do that. So here is the following chart. Here is the following values. Let's put this in general. Let's put this one in general like k square. Here is the following values: 0, 1, 2, 3, 4. This is enough. So reducing this one to mod 3, taking the following values: 0 becomes 0, 1 becomes 1. Replacing k with number 1, I get 1 here. I get here 2 square, which is 4. I get number 1 as a remainder because 4 plus 1. I get 3 square, which is 9. I get 0 here. 4, which is 16. 16 is 1 more than 15. The remainder is 1. So this one is have a kind of pattern. This one is keep going all the way down like this: 0, 1, 0, 1, and all the way down. Okay, so which means this k square belongs to this set 0 and 1. A problem, but we don't have 0 and 1 here. We have minus 1 as a remainder, which is clearly it's impossible. It's impossible. I'm putting this sign like this, which means I mean the contradiction. Okay, so which means a is not a even, n is a odd. N is a odd. Okay, now we have determined the parity of n, which is odd. Now let's erase this board and move on to the next step. We know n is a odd from previous proof. Okay, now before we get into proof, I'm going to check when we have m equals 2. Okay, plug in number 2 into this one. I get here capital A. I get 2 plus 3, which is 5, which is 5 to the n plus number 1 over 3 is multiplied by 2, which is 6. Okay. Now Elwari proved n was odd. Okay. So this one, it was odd. So which means I'm going to factor out these two terms on the form of the product, since we have n is odd. Okay. So this one is giving us 5 plus number 1, factor 5 to the n minus number 1 minus 5 to the n minus 2, and all the way down to number 1, like this. Okay. All is divided by 6. So we get here 6 here. We get 6. It will cancel out from numerator and denominator. I will be left with this expression. Okay. Now the question, what's the parity of this one? Is it odd or even? Okay. This one is odd because this one is representing the oddness of this one. Since n is odd, which means we have odd terms here. Okay. And also this one is odd always. This is odd. Okay. Let's take an example. If you take n equals 3 here, so we have 5 to the 3 plus number 1, factor out this one on that form right here. So I get 5 plus number 1, factor 5 square minus 5 plus number 1. Okay. So we get the same thing. We get odd terms here, and also this term is odd because this one is 25 minus 5 is 20 plus number 1, which is 21. Okay. Whatever the odd you choose in here as an exponent, you get this one is an odd, and also it has an odd term. Okay. This is what happened here. If this one is an odd, we have proven our setup on this value, just m equals 2. Okay. We know this odd, which means a is an odd. Now we have proven the first case when we have m equals 2 is an odd integer. Okay. You might ask why I'm starting with m equals 2 as a value. I will let you know in a little while. Okay. Now let's go ahead and get started with the proof. Now we have collected enough information here. Now we are ready for the proof. Okay. We are going to assume this one, by the way, of contradiction is an even. Okay. So by the way of contradiction, suppose capital A is an even. So which means let's set capital A equals to k. Okay. Let's replace a capital A with 2k here. Number 3 plus m is raised to the n as an exponent plus number 1. This term, it will be multiplied by capital A, which is 2k. I get 6 m k. Okay. We know the right hand side of this equation is even, which means the left hand side of this equation must be even as well. So m must be even. Why m is even? Because odd plus even is given as odd. Odd plus number 1 is given as even. Okay. So m as an even number is going to be written on this form: 8 plus 2d. With d is super equal to 1, you know d is a natural number. Okay. Here is a nice fact here. You might ask why I'm writing this one on this form. Why I'm not writing m on the form of 2d, for example. Okay, I will let you know in a few seconds. If I'm going to consider this one, which means I'm going to check a few values of m before we get to this one, because if d equals 1 here, I get this m equals 10, but we need to check the value m equals 8 and 6, 4 and 2. We already checked 2, it was okay. Okay, we don't need m equals 2 here because already did that. That's the reason why I have proven m equals 2. It was fraction was odd. Okay, now we don't need that, because if you're using m equals 2 here, you are not taking you to the solution. You will have a problem while solving this one. Okay, now we will have okay. Now we will be okay. Okay, now just the thing that we need, check the values. Now check the following values: m equals 4, 6 and 8. So this one, this proof, when we have m is super equal to 10. Okay, this one, let's put this one together with this one. So this one we are going to use it after we check this one. Okay, let's check that here. When we have m, let's check when we have m equals 4. We are always working on this assumption because we have chosen this one is even. Okay, let's replace m with 4 here. I get 4 plus 3, which is 7. I get 7 to the n plus number 1 equals 6 is multiplied by 4, which is 24k. Okay, I'm simply going to use the mod 3 because we have 24 is divisible by number 3. This one is a congruent to 0 mod 3. Okay, so this one I'm going to split this 7 into 2 parts. I get 6 plus number 1. You know 6 is divisible by number 3, which is 0. So I'll be left with 1 plus 1, which is 2. This one is giving us 2 is a congruent to 0 mod 3. This one, it's clearly a contradiction. It's impossible. Okay, let's check the next value. M equals 6. Doing the same thing here. 3 plus 6, which is 9. I get 9 to the n plus number 1, which equals 6 is multiplied by 6, which is 36k. Okay, since we know 36 is a multiple of 9, so I'm simply going to reduce this one to mod 9. Okay, so I get this one is a congruent to 0 mod 9. Also this one will be 0. Okay, this is 0, so I will be left with 1 is a congruent to 0 mod 9. I get here 1 is a congruent to 0 mod 9. This one also is a contradiction. It's impossible. Let's check the final value. M equals 8. Okay, so replacing 8 with this one, I get 11 to the n plus number 1, which equals 6 is multiplied by 8, which is 48. I get 48k. I'm going to reduce this one to mod 8. This is an appropriate one. Okay, so we know 11 to the n is the same as 8 plus number 3, all is raised to the n plus number 1. This one is a congruent to 0 mod 8. This one is clearly is 0, 8. I will be left with 3 to the n is a congruent to minus 1 mod 8. Okay, if you are going through the chart, okay, you will find this one 3 to the n belongs to 1 and 3 only as a reminders. Okay, so we have absence of minus 1 here, which is clearly it's a contradiction. I'm not going to do the chart here. You will see the same thing in the next step. We will have a same chart on this value 3 to the n. That's why I'm not going to repeat it again. Okay, so we already found the contradiction on these values as you see here. Now we are going to use this general proof in order to find a big contradiction. Okay, so now let's get rid of this one and move on to the next step. I'm going to replace this value that I have here as a fact and put it here and to see what's the next expression. Okay, so replacing m with these values, I get 6 is multiplied by 8, which is 48 k plus 2d is multiplied by 6k, which is 12d plus 12d k. Okay, this one equals m will be replaced also with, let's do this one right away. M will be replaced with this one. I get 8 plus 3, which is 11 plus 2d here is raised to the n as an exponent plus number 1. Okay, so since we get 48 here, we get 12 here, so number 4 will be divisible by this one. Let's reduce both sides of this equation to the mod 4. Okay, so this one is given as, this one is a congruent to 0 mod 4, because left hand side of this equation is a congruent to 0 mod 4. So let's check with this one. So let's reduce this 11. 11 is the same as 12 minus 1. 12 will be 0. I will be left with minus number 1 here. Minus 1 plus 2d, all is raised to the n plus number 1. Okay, let's work a little bit on this one. Let's take minus 1 out of these things here. I get minus 1 here is raised to the n as an exponent. This one I will have number 1 here minus 2d, all is raised to the n plus number 1. Okay, so I just took minus number 1 out of these things as a common factor here with this n. This one is a congruent to 0 mod 4. Okay. Now let's take this number 1 to the right. This becomes -1 here. Now if you remember, I already proved n is an odd, which means this minus number 1 turns into -1. With this -1 will be cancelled out each other. Okay, so I will be left with 1 minus 2d to the n, which is congruent to 1 mod 4. Okay, here is a nice thing here. I would be remind you about the binomial expansion here. We'll have 1 plus x all to the n 1, or n choose 0 plus n choose 1 is multiplied by x plus n choose 2 is multiplied by x squared plus n choose 3 is multiplied by x cubed, and so on and so forth. Okay, I'm going to apply this binomial expansion on this one as we have, because you have a number 1 here, we have this one, it will be replaced with x. Okay, so let's put this one like x or minus x, the same thing. Okay, I will have number 1 as a first term, or n plus n choose 1 is multiplied by this one, which is minus 2d, plus the third term, which is n choose 2 is multiplied by minus 2 squared d squared. Okay, plus the third term, I will have n choose 3 is multiplied by minus 2 cubed is multiplied by d cubed, and so on and so forth, and all the way down. All this bunch of these terms, it will be congruent to 1 mod 4. Okay, as we have here. If you take a look here, from here to here is 0 mod 4, because we have number 2 square here. Everything is divisible, each term is divisible by number 4. Okay, all the way down. So I will be left with this one, and also number 1 will be cancelled out from left and right. I will be left with this one. This n choose 1 equals n, because we know n choose 1 equals n factorial over 1 factorial is multiplied by n minus 1 factorial. I'm going to write the numerator as n is multiplied by n minus number 1 factorial over 1 factorial becomes 1, n minus 1 factorial. So numerator and denominator will be cancelled out by n minus 1 factorial. I will be left with n, so which I have here. Okay, so I will have the following. I will have this term, which is minus 2dn. Minus 2dn is a congruent to 0 mod 4. Okay, since 4 not divides 2, and also 4 not divides n, because n it was odd, it's impossible to have odd in numerator and even in denominator. Okay, never ever even divide odd. Okay, which means 4 must divide d. Okay, if 4 divide d, which means d is a multiple of 4. Okay, so which I will have d equals 4 is multiplied by p. Okay, like this. Now let's take this value of d and insert it back to this one here. Okay, so I will have here, I will have m equals 8 d. I will get here 8d, 4 I get 8p. Okay, so I get this one, and then what I'm going to do now, I'm going to take this found fact and insert it back to the original expression to see what's the new expression. Okay, what I'm going to do now, I'm going simply to replace m with that value that I found lately. Okay, so I will have a is multiplied by this term, so which is 3 is multiplied by this one, which is 24. I get 24a, capital A, plus 8 also is multiplied by 3 is giving us also 24 p, which equals to this one, which is m will be replaced also with 8 plus 8p. I will have 3 plus 8, which is 11, plus 8p, all is raised to the n as an exponent, plus number 1. Okay, I'm going to reduce both sides of this equation to the mod 8. Okay, So this one is a congruent to 0 mod 8, because we know left hand side of this equation is divisible by number 8, okay, which means the right hand side of this equation must be divisible by 8 as well. So I get here, reducing this one is always given as 0 because it was multiple of 8. Also I can work a little bit here. Again, split this 11 into terms. I get here 3 plus 8. Also this 80 will be 0. I will be left with number 3 here, which means 3 to the n as an exponent, plus this number 1, which is a congruent to 0 mod 8. Okay? Taking this number 1 over to the right of the congruence, so I will is equivalent, I get 3 to the n is a congruent to minus 1 mod 8. Okay? So I have ended with this nice expression. Now what to do? I'm going to go through quick chart to check what's the possible values of 3 to the n as a reminders, okay, in the chart. Let's do that. So I get here following values. I get, for example, n. Let's take the general case, k, and 3 to the k. Here is the following values: 0, 1, 2, 3, 4, 5, so on and so forth, okay? So, of course, we are going to reduce this one to mod 8. I get the following values: 3 to the 0, which is 1, 3 to the 1, which is 3, 3 squared, which is 9. Now we will have 1 more 8, which is 1 in the remainder. 3 to the 3, which is 27. 27 is 3 more than 24. The remainder is 3. So this one this one keeps going all the way down like this: 1, 3, 1, 3, and all the way down. Okay, which means this one belongs to this set. 3 to the 3 belongs to 1 and 3 only. But we don't have here number 1 or 3, so which means it's a contradiction. Which means what we have contradicted? We have contradicted our assumption, because we have assumed A is an even. At the end of the theorem, we found the contradiction, okay? Which means this fraction is not even number, but is odd number. So I have done this problem for you guys. If you have any question regarding this problem, just put it in the comment section below. If you have any different method, just put it in the comment section below and let me know what you get. So by the way, don't forget to hit the subscribe button and support our channel. And thank you for watching. I will see you next video. Bye.